Okay, we talked earlier about quantum computers, went into a lot of depth, and now we're going to talk a little bit about the foundation that quantum computers reside on. They are built on a foundation of the physics of quantum mechanics. So to really understand and comprehend the benefits and the pitfalls of quantum technology, we have to understand a little bit about quantum mechanics. Now, quantum mechanics is the physics of subatomic particles, their behaviors, their interactions, or the things below the level of a full atom. Now, there is some behaviors and some interactions with full atomic particles, but you sort of know all about that, so that's the stuff you learned in high school, so we're not going to go into that stuff. We're going to deal specifically with quantum mechanics. So in quantum mechanics, we are interested in electrons and photons and their waves, and even smaller elements like bosons and fermions and quarks and other dimensions like quasiparticles. At these levels, particles and energies display unique states. That is, they display waves. States that can be used to represent real-world data, just like we use electromagnetic fields to induce and use binary states in a classic computer. Quantum computers use these quantum states to process data very, very fast, using quantum behaviors, math, and representations to get the job done. Particles, at their very core, behave like both particles, as we would expect them to, and waves. That's probably not something we would expect. So what do we mean by waves? Well, me talking to you is producing sound waves, and those waves, which have variance and amplitude and frequency, they're traveling through the air, and your ears are picking them up, and your brain is processing the information to turn it into a usable format. So you are, in effect, using the quantum computer in your head to process waves. And this is similar to what we're doing in quantum computers. Now, critical to this is the notion of wave collapse and wave functions, and we'll get into that a bit later. Particles and their wave functions are important because it leads to very important properties like superposition. Now, it's best to avoid arguments on the existent nature of superposition. For example, is it physically real or not? The whole Schrodinger's cat debate. It doesn't matter. Quantum computers use it, is math described, and we can prove it exists, and we'll show you something about that a little bit later on. When wave parts interact due to reflection, i.e. interference with other waves, they exhibit superposition, and that's what we're going to show you. Now, superposition is the foundation of deeper representation of states in quantum systems. And this is the foundation of the greater speed of computation with lower energy levels in quantum computers, along with other elements like entanglement. As such, all quantum particle behaviors can be described by a wave function. Now, wave functions, what the heck is even that? Well, wave functions are mathematical functions that describe the behavior of waves, surprisingly. Quantum particles exhibit particle behavior and wave behavior, or quantum dimensional levels, and this is what we use when we go to process information in a quantum computer. Now this right here is a superposition wave function. Superposition is both states at once. So in a bit we have a state of 1 and a state of 0, and in a quantum computer we have a state of superposition or both at the same time. Wave functions apply to qubits and thus to measurement or manipulation of quantum states. There are many types of wave functions in quantum computing, like single or multi-qubit, superposition, entangled, and a bunch of others. In this particular wave function, a superposition state of a qubit is set, that's 1 and 0, along with the probability amplitudes of each state at collapse, which happens at measurement just like the sound waves that I'm emitting right now. They travel through the air as waves. They hit you where you're sitting in a particular position, and at the crest of that wave is the sound that you hear and the amplitudes and frequencies and the other waves that form the primary sound wave. And your brain is interpreting it at that position, at that point in time. And it's different from the person sitting next to you or the person sitting next to you. They may hear the same thing, but the wave position is different, or their position on the crest of the wave. And then once it is interpreted or measured by your head, it's gone. There is no holding on to that position. You can think about it in your memory. You can maybe record it and hear another similar wave, or you might even hear an echo, which is another portion of the wave. But it's not the exact same point on the crest of the wave for your position, for your dimension of time. And that's sort of what we mean by the wave collapses. The symbols in this formula are probabilities of the wave being in either state at collapse. Now think about that, the probability of the wave being in a particular state. So in a superposition state, which is both 1 and 0, we don't really know what position it's in. It's in a superposition state is the position that it's in until we measure it. But the minute we measure it, it's in one state or the other. Now what's interesting is when it's in superposition, is it has a probability of being in one state or the other at the collapse. This means that superposition states as probabilistic realities. They exist dimensionally. We don't know how deep they exist dimensionally, but we can use knowledge of superposition for computation, similar to how not knowing about quantum mechanics didn't stop us from creating and using classical computers. If you accept that waves can be composed of other waves, which they can, I can create multiple waves. Obviously sound has different waves, lengths, and different wave positions, and we can layer them together. In fact, we can use sound to cancel sound. Well, if you accept that notion, then when two waves combine, they can represent a superposition of states. And I just mentioned one of them. The use of sound waves to cancel out other sound waves. Wave interference is this kind of thing. This is what we're looking at when we talk about wave interference. So, wave functions describe the behavior of quantum particles, just like a mathematical model of current and voltage equations describes a transistor flowing current or not in a classic computer. The wave function provides the elements necessary to calculate and measure and interpret a quantum particle state, be it 1, 0, or superposition. We can use a quantum algorithm, or code, and a wave function to manipulate or read the underlying qubit/particle states. Now, qubits don't produce a wave function. The underlying particles do. But qubits use these underlying wave functions as a control and measurement mechanism, just like bits and logic gates use a transistor states in a classic computer with mathematical models and representations. For example, a superposition is a state described by a wave function in a qubit in a quantum gate. The values in the wave function describe a probability distribution of potential quantum particle states. Think about a probability distribution of the kind you see in statistics. Now that probability distribution represents the position on the wave. And this is used by quantum computers for processing, etc., etc. Now we don't care about base states today in classic computers. I mean, you won't think about which position the bit is in as you're using your computer. You won't care about the same thing in quantum states for quantum computers in the future, because we're only at the machine code stage in quantum computers. Now eventually quantum computers will move to higher dimensional states and direct applications like sort of like we use ChatGPT now in classic computers today. I mean, we're not thinking about the state of the transistor when we're doing that. We're just using the application. So eventually that will happen in quantum computers. Now, let's talk about the slit experiment and superposition. When shining a light or an electron beam toward two slits, scientists found that the pattern on a detector screen in back spread out and gapped. Now, if photons or particles, it should have been concentrated in two spots, not spread out and gapped. The gaps arise because the photons or electrons exhibit waves, as well as arriving on the back of the screen, of the detector, the particle detector. So both particle and waves, it exhibited both of those behaviors. Now further, the gaps are the high and low densities depending on where the position of the photons are on the wave, and as a result of the interference, indicative of superposition. Now you can sort of see this. So on the right is the slit experiment using a laser. You can note the gaps between the light points or the density on the detector. On the left is the pattern of two waves colliding. So again, note the light and the dark areas where the waves catch the light, even on the same wave crest. Those two things are the same. So you should be able to see in your mind now that waves have high and low points on the same crest, and at the point of measurement is where you will see either a high or a low point of that wave. Now this is because waves add together or offset where they hit. So if waves are composed of waves, then they can offset, they can be in superposition, so to speak. Now remember my sound example. As the waves travel from me to you, they self-interfere and are composed of waves of different frequency and amplitude, highs and lows, and you don't know which one you get until you hear it and process it in your head, and then it's gone. Notice in the picture the crest of these waves has high and low points, depending on where you are on the crest. Now you can imagine yourself being on a shoreline when that wave hits. And that particular point where you're standing, where that wave hits, is either going to be high or it's going to be low. You don't know which one necessarily until it gets there. And then it's gone. The right image is what's known as an interference pattern, made by waves from a single source or a beam as they collide. Once the crest hits or is viewed, it vanishes until the next wave, and that's what we call collapse. Now the waves of a photon particle can be both light and dark at the same time because the photon that passes through the slit is interfering waves that offset or add to the original. The photon exists in multiple states at once, just like a wave created on water for each moment of time and each position or measurement, i.e. superposition, all with a probability distribution. Now you sort of understanding how quantum mechanics fits into quantum computer portion we talked about before. Now here's where we get to superposition. When the scientists placed a measurement device just past the slits, the interference pattern, so that was just past the slits, between the slits and the detector, the interference pattern disappeared. And 2 lines of particles showed up on the detector, one for each slit. No more interference pattern, apparently just because of the measurement device. The waves collapsed, seemingly because of the simple act of measurement. Just like you hearing the sound of my voice, and once you hear it, the waves collapse because you're listening to it. This is Schrodinger's cat. The act of measuring a superposition state causes the wave to collapse. This verified that the single particle sent toward the slits was in a superposition state and that it collapsed when it was measured. Now, no one knows for certain why this occurs, but I have a deep dimensional theory and some potential applications of this, and I will discuss that in the investment portion this afternoon. So here is part of a quantum algorithm. It implements a Fourier transform via an Hadamard quantum gate applied to a qubit, so it instigates superposition. The Fourier transform is a signal transformation model that converts a signal that is a function of time, i.e. a wave, into its frequency components, so subwaves or base states. Here it is used to find the period of 2 points on the function, i.e. states of a wave that represent data like frequency and amplitudes, or the high and low points, or states of superposition. This is how quantum computers use wave functions, the math, to measure and instigate qubit states. Okay, waves collapse, or more accurately, they stop. And at the point where they stop, or are measured, is where their existence becomes real for the context of a perception. You hear me when I speak, and then you don't when I stop, unless you recorded it or hear an echo. In short, when we see or hear a wave, we can never see or hear the exact position on that wave ever again, although we can hear echoes in some form, which are other parts of the same wave, and or subsequent waves or brand new waves. Thus, superpositions collapse when they are measured or perceived. Until this existence, the waves exist and propagate in multiple states. So let's talk about superposition, but first we're just going to go back and review a little bit. We talked about quantum computers and how they trap and use quantum particles that have states that we can instigate with lasers and electromagnetic pulses, and that we can measure, how these systems are encapsulated as qubits and represented in algorithms as quantum gates. We talked about wires connecting qubits to control mechanisms, code that implements the actions, and a bit about potential memory and persistent data. We discussed quantum mechanics and wave functions and how they collapse, and now we're going to move on to superposition and entanglement.